So our topic this week in Geocomputation with R is Chapter 8, the input and output of data to solve problems. I thought it's interesting that we've gotten to Chapter 8 before we talk about real world, say, data sets. But there is some complexity here that's necessary, and the previous chapters laid some of the groundwork for understanding the care that has to be taken with geospatial data types, the attributes, and we'll get into some of the other complexities of the available data sets out in various services. We'll encourage readers to put some time into identifying the resources and the data sets that are available and how to retrieve them programmatically. There are many file formats available. Each of the file formats has pros and cons. And the end of this chapter nicely moves us towards a Chapter 9 discussion on making maps. So this Chapter 8 is really the heading or the beginning for most any geospatial project. A practitioner, of course, part of what you deliver as value is an understanding of what resources are available. So this chapter presents a sort of a survey of a handful of lists of resources, and it's a bit of a tour. The packages we'll use, as before, are SF and Terra. I've included dplyr and ggplot to do some manipulation, and SP data is included as a source of sample files. What's that? Okay, right off the top, there are open data resources, which essentially means free for use by anyone, at least with access through the API connection. In some of these cases, well, in many of these, you do have to go to the portal and register your email and get a token. But these sources are, say, clearinghouses or libraries of many kinds of temporal and geospatial data. The first one, data.gov, is largely US data sets on the economy and on natural resources and all sorts of other topics. The second one, geoportal.org, is a well, in fact, I think we can open it real quickly. It's got this beautiful little animation and even a search tool, which is just lovely. So if you have a subject you're interested in, the Geos portal allows you to search on that subject, and it will pop up matching geospatial data references. Copernicus is satellite-based imagery from a network of satellites, and NASA CDAC is also largely different kinds of satellite imagery. Just recall that some of this imagery is maybe LiDAR or at certain wavelengths. Some of it is optical wavelengths. Some of it is broken down by different kinds of colors to look at vegetative state or snowfall, weather, all sorts of interesting things. And the last one listed, at least in this open data index, the EU Inspire data set. Here again, it's a geoportal with a browsing tool to look at just an incredible a number of EU member state data sets. They also list the US Geological Survey Earth Explorer, which is a handy way to get landmass information. The author notes that exploring data sets interactively, as you do with Earth Explorer, is a handy way to maybe zoom into a part of the world. I'll zoom into my part of the world here in Chicago, and search in some ways for imagery based on timestamp or subject, and extract just the elements you need for that part of the earth. But although that's handy for exploring data sets interactively, we really need a scripting way to download data reproducibly, and the best way to do that is with code. One way to demonstrate that is to do a direct download. So here's an example of a R download, where download file is provided with a URL to a web portal. A destination file is say the local name of that file when we get it, and a mode for downloading. R has an unzip command, which would unzip that file locally in a folder, and then SF's read SF can read that shape file that was in the zip file. We'll step next into more sophisticated ways of getting data from these portals and others. Downloading is a sort of a one-time shot. An API call is a more of a web handshake between say a server serving up data and our client application. And there are a number of convenience packages we're going to talk about that simplify the API calls and make it a little easier for say people to both to get the data that you would like to have, but also manipulate that data in a convenient way. Okay, among the convenience packages that they highlight, there's a couple here that I really love to use. The OpenStreetMap project is a huge effort to gather the open source data sets, things like hiking trails and streets and park boundaries and all sorts of useful data can be pulled through this OSM data package, and with the parameters in that package, it's very easy to pull data that you're allowed to use without say subscribing to a service or say resorting to a closed system. Other tools, Geodata has administrative and elevation and interestingly world climate data. Our Natural Earth, the R-OpenSci community administers and the maintainers of this package provide an interface to a library of natural resources, map resources. NOAA is a climate data source, the National Oceanic and Atmospheric Administration. And although this is a US agency, this is a global data set. It's very, very nice for getting weather data. Heidi Census and Tigris are kind of related. Tigris is shapefile maps for all sorts of US jurisdictions. So census tracts counties, congressional districts, and states. All those in varying levels of detail are available through Tigris. And then Tidy Census adds quite a bit of demographic data on top of the Tigris shapefiles. CAN Census, much like Tidy Census, CAN Census provides Canada's demographics. Eurostat for many EU, say, demographics. Also GISCO, and then there's a number of other international databases available through IDBR. We had a Tidy Tuesday a couple of years back on a data set from British Columbia related to bears and bear populations from BC data. Brazil has a collaborative effort to provide APIs to open source data through GeoBR, Czechia, and then there's this other global summary weather data, GSODR, that's very handy to get weather over time at any point on Earth. A note here, each data package has its own syntax for accessing data. The package vignettes in R are very good, and in some cases, the packages like Tidy Census has its own, even a free textbook that is accessible. So the author walks us through some examples. Our Natural Earth is handy. It's being revised right now. Our Natural Earth, any countries will bring back an SP object, not an SF object. But those SP objects can be converted to SF objects. One way in the SF package is to say STSSF. So in this case, we're using Our Natural Earth to grab US boundaries, and there's a default precision involved here. The second example is raster data, grabbing monthly precipitation with a spatial resolution of every 10 minutes or about 18.5 kilometers at the equator. So this World Climb Global, grabbing the precision data set with the 10-minute resolution. When I run this, it pulls a rather large file down to a temp directory, and this is raster data, and it comes down as spat raster, so it can be used with a Terra package. The next example is OpenStreetMap. In this case, we've grabbed a bounding box. I picked a Chicago bounding box, so it's a square that represents the maximum extents of the city boundaries. And we're adding an Osmodata feature for, if you look at the help for this, leisure is one of the categories of features, and we're going to grab the park boundaries as shape files. And this is a very convenient way to get all the parks in the city of Chicago. One note here on OpenStreetMap, it does have a rate limit. So you can only hit that so many times in a certain period of time. There is a way for larger projects to use OSM extract to programmatically cache files into a local directory, so you can keep them over time and only add what's changed. The OSM, or the OpenStreetMap data source, and the wider ecosystems are available globally. They're very conveniently free. So in that way, maybe more desirable than some of the other mapping services that you have on your mobile phone. And what's nice, OSM data is constantly improving. There are submissions coming in from a huge army of volunteers all over the world. They encourage citizen science and make contributions back to the digital commons. It's worth mentioning here that SP data and other packages here also have built-in data sets in the R package. It's say a static sample of a data set. And here's 4 ways to load, well, in this case, the world data shapefile. One of them is to load the library, or you could load just the world data set by calling out world and the package using the data function. Or you could retrieve the data set using the 2 colons. And you could read SF using system file. I see a hand. I'm sorry, I missed. Yeah, go ahead.
Yeah, no worry. Just like quit advertising for OSM, you can also be a contributor of OSM. If you see error in the data set, you can register by an email address and go like just type OpenStreetMap. You will come to the one of the most basic editor, which is called ID, but you can also edit it through your mobile phone. Like either if you are using, like, let's say, I think on iOS it's called GoMap, and you have another one on Android, which is probably Vespucci, and there's plenty of others that I'm not aware of. But you can edit the data also and correct it if you found errors. And feel free to contribute. I contribute personally, and it's not difficult. It's not hard. You have plenty of good resources online to help you, and I can provide link letters. But it's important, like, to when you are using the data, to contribute. You can also contribute like on all of the tools that's behind. You can also contribute if you are interested. You can contribute on the data side or on the computer side, on the software side. That's it. That was.
Oh, thank you. Thank you.
Easy to do.
That's fantastic. I see Ryan's joined us. Welcome, Ryan.
Thank you. Appreciate it. Joined a little late, but very interested in this conversation. Thanks.
Yeah, fantastic. Okay, yeah, I'll add OSM data has been handy for hiking trails, things that change from place to place and time to time. It's just fascinating what's out there. Okay, they note here also, besides retrieving data through packages and APIs and as sample data, there's also a way to use like an Excel list or maybe a list of locations and transform that data by geocoding it, which essentially means to take a list of addresses, so street addresses or postal addresses in some way, and convert those into latitude and longitude coordinates. And obviously, when you have lat-lon and some sort of projection, then presumably you can have those points or the polygons on a map. There exist a number of online services, or have for over the past decade, for geocoding into coordinates. Some of those now cost money. So the way the packages had been written maybe has had to adapt, because what used to be free is no longer free. The text recommends today the use of the tidy geocoder package. It interfaces a number of backend services and has ways of creating the key or the token to register your use of those services. Some of the services are rate limited. They also mention here a reverse geocoding. So if you have locations on a map and you want to go backwards to addresses, that service is also provided through some of these systems. So Tidy Geocoder is worth say checking out, and it's more comprehensive than most say other services that had been maybe built for just one API connection. All right. Okay, moving on. So when we talk about open data and all these services, the industry has recognized that there's a need to standardize these interfaces and standardize the naming of entities in these files. And there does exist an Open Geospatial Consortium that writes specifications, or OWS, to standardize web features, map tiles, say the language for coverage, and even how we process like raster images. Map servers like PostGIS have adopted uniform protocols so that when we connect a data source to a renderer, it behaves in a standardized, predictable way. They provide an example in here of an entity that complies with OWS. In this case, it's FAO, the Food and Agriculture Organization of the United Nations. And one of the protocols for getting data, what it looks like is a base URL for the organization, an endpoint, just think of it as a server within the organization, and then a URL query connected by say a string. So in this GET request, there's the base URL, that endpoint path or that server, and then the query itself. And what that brings back, well, at its simplest here is the result of what you've asked for from that server. So there are a number of geographic web services that use this sort of protocol as an API connection to pull data. The available names of the data depend on the accessed web feature service, but FAO has a huge number of say global agricultural data sets and over time, and they provide here then a way to look at the result of that. There is a package OWS4R that was specifically developed to work with OWS services. So FAO is one of many organizations that offer their data sets, in this case on farming, but through this standardized sort of interface. So along the lines of that standardized interface then, when you get the file, which we all know can either be vector or raster data, that could be pulling that data from a live spatial database. Maybe imagine in chapter 1, we talked about a bus stop, and maybe you're looking at a city and the buses traversing from bus stop to bus stop in a city. That's essentially a spatial data set. And there are ways essentially in real time to query a spatial data set, as PostGIS. So what I've mistakenly called GDAL for years is, I suppose it should be GUDAL, according to the book.
The old people said GUDAL, the young ones said GDAL.
Okay.
The people like in the know it's GU, but everyone said GDAL now. I don't think it's matter too much.
I'm
it's kind of an inside joke.
Okay, good, good. I know that under the hood, that the geospatial data abstraction library, or GDAL or GUDAL, that it exists makes the conversions possible. So the R community, the Python community, and many other communities can work across file types and convert from one type to another using these methods that have already been laid out. In the trade, it's very common to encounter Esri shapefiles, for example. Though they're older, they're multi-file, they have some size limitations, technically proprietary, but it's possible to convert Esri shapefiles into KMLs or into GeoJSONs, and these conversions of files across formats happen because GDAL or GUDAL has worked out a means of bridging from one to the other. In fact, founded in 1994, so this has been going on for almost 30 years. Open file formats, and we'll cover some in the examples, have some advantages, particularly because the standards are published, so everybody can see the standard. They ensure transparency, and they open up the possibility for users to further develop and adjust the file formats for very specific needs. We mentioned real-time or weather or say machine learning applications, and open standards allow many people to put their brains together to arrive at solutions and then implement them in many different places. Okay, so when we load the file, like read SF, what we're doing when we read that into an object, we're reading that into RAM, into our R session. Some of these geospatial files, especially rasters, like satellite imagery, some of these files are very, very large, maybe even larger than RAM. So there are some techniques to be aware of, and maybe some conversions that need to happen. I did pull here. There's a SF command called stdrivers. I think it's in SF. I'm not sure. We'll look here. Oh my. Well, it's in one of the packages I have loaded.
Yeah, it's an SF.
Okay.
If you ask the namespace, you will get it. It's because like you worked on R Markdown, so it probably does not load it in your session.
Fair enough. So for my on Ubuntu, my GDAL installation, I'm seeing that there are like a couple hundred file types that my system is able to recognize, and for each of them, I'm able to write many of them, copy. There's this is raster, so is it a raster type or is it a vector type? Many of these, like a FITS, can be a raster and a vector. And then the say the owner of the standard is listed in this ST driver. So you can get a snapshot of, for your version of GUDAL, what file types it's able to handle. But this is matured to handle a huge number of file types. So there's a lot happening under the hood with vector data. When you say read SF, it's looking at the file name extension and making some assumptions about kind of file that is and validating that. And it presents some information as read SF happens. Unless you say quiet is true, it's going to tell you some things about what it's assumed about what kind of file that is. For some drivers, a DSN could be provided as a folder name. In some cases, you need to give access credentials if you're plugging into a PostGIS database or a GeoJSON string representation. So this read SF has a number of parameters available to be able to access many kinds of files. Some file formats can store many data layers. By default, read SF provides the first layer of the file, but you can use a layer argument to pick out any layer. I thought it was interesting. You can also use in read SF SQL query. In this case, we're going to select from the file source up above, all columns from the world data set where the name long is Tanzania. And it brings back a shape file that we can plot, and it looks like Tanzania. So I was impressed that you could use SQL and read SF. If you don't know the names of the columns in a data source, that old SQL trick where you could just say select star from world where ID is 1 will give you the first row and you'll see all the columns. Another approach, maybe we're interested in this map, but we want the neighbors. Like we want to understand where this is in the world in the context of its neighbors. And so what the author's done here is created a buffer around that object and asked for the geometry as text, as well-known text. And then they can read SF with this well-known text filter that is that original SF object plus the buffer. Again, this is much like the SQL up above. This creates a text string that grabs all of the neighbors. Now, what's odd though about what's plotted here, what it should be grabbing is, and I wonder if my buffer is too large, because I wanted 50 kilometers and it's grabbed the whole world. So this is a mistake. I'll have to fix it, but it should be grabbing the countries that are just the neighbors of Tanzania. I'll have to look into that. Read SF also reads KML files. A KML file is a bit like an XML file, kind of related to the creation of web pages and data transfer. So I think I've run into KMLs in like in your Google history. For example, you can download your history in using Google Maps. And KMLs also have many layers. So in this case, you can download a KML file. You could download your own Google history and then look at the layers of your KML file and see. So in this case, it has the Google campus on the KML file. And we could look at one layer using the layer parameter. In this case, the place marks is the first layer, and we can plot that. And there are 3 points, I think, sitting on the Google campus in California. Switching to raster data. As with shape files, raster data can also have many layers, particularly when we've got different wavelengths of light. And in our example here, we're just going to grab from our sample data a raster and look at the first layer, and you get this pretty image that if you use your imagination, these are valleys in, I think in Utah, in Zion National Park. The same sort of rast command also works if you want to read a multi-layer file. When I just look at it here, it gives the names of the individual layers, Landsat 1, 2, 3, and 4. So these examples read spatial information from files stored on the hard drive, but GUDAL or GDAL allows searching from online sources directly. They note here that when you do that, or when you get instructions to do that, this VSI curl gets added to the path to the file. So you'll see in this URL, this VSI curl is ahead of the HTTPS for a file, and that provides the rast function with enough understanding to go there and grab the file directly from the server in the cloud. And here again, it says snow consists of, it's this many dimensions and that resolution as a TIFF. So in this case, because the input data is COG, we're not actually reading the file to a RAM. We're creating a connection to it. What's nice in raster is with the connection established, then we can operate on the connection using the extract function, and that stacks the commands to just get well, in this case, the snow, say precipitation for December in Reykjavik. This longitude and latitude is Reykjavik in Iceland. So the earlier raster is say a global monthly snow probability for 12 years, and extract allows us to pull in for just Reykjavik. The VSI curl prefix works not only for rasters, but for vector files. I think it's noted here, though, in rasters that the files can be huge. So being able to build or to stack the commands and just extract what you need is really handy to get around RAM limitations with your computer. Besides VSI curl for web addresses, there is a VSI zip to read zip archives without decompressing, and VSI S3 for reading from AWS S3 buckets. And there's this great website. In fact, I think I can open this guy. Okay, so the GUDAL virtual file systems is at the gdal.org website, and they talk about other handy techniques to get around virtual file systems to get around RAM limitations that you encounter quite often. There's a hand. Go ahead, Olivia.
Yeah, just it's also like allow you to not waiting hours to download one file.
Yeah.
So sometimes you just need like a raster. You need like a raster can be very big depending of your internet connection. It can take time to download. So just specifying the piece you need save money on a lot of side. your times, because your times is money. The internet connection does something. And everything. So yeah, it's a very neat. I think it's new on GDAL. I'm GUDAL, whatever you call it. I think it's you need to have like a GUDAL version superior to 3.6, maybe 3.5. I don't know. So you need a new GUDAL. I can't remember which version it is, but it's great.
Yeah. A lot of great stuff. Okay. They mentioned data output. So whether you're caching your results or maybe sending your data file to another app, maybe, and this is quite common, maybe you want to use QGIS or Esri or some other mapping tool. Maybe you'll do some of the processing in R and the rest of the processing in a mapping tool. It's important to know how to output the files. There are considerations in your choice of the file format to write into. The speed of writing the output to storage is one. The size of the objects and how you move that thing. The speed of rereading the object later, if it's compressed in particular, the data type, the object class, and then whether you need layers or not, are all considerations for deciding on a file type. Write SF has an interesting parameter. If you're working like in vegetative state and interested in characterizing the growth of a forest or a crop, you may take the red and the green and do calculation and then add an additional layer to the say to the file that you started with, and you can append another layer to the file you started with. Write SF and STWrite are in the same SF package, but they have very different default parameters, and we'll touch on that in the examples at the end. Similarly, in raster images, a write raster normally saves a spat raster object using this FL4TS say protocol as the default data type. And there's a chart of other data types. You may choose a different raster encoding though, because this FLE4S is equivalent to large floats. So the numbers are saved with a lot of trailing digits, and it may be more efficient to choose a different protocol if your data is in categorical or integer type values. You can get a much smaller file if you choose a different raster data type or raster encoding. And think of it as different. It's kind of like precisions, but not exactly, because if you've got integer or categorical data, it's just as precise. It's just categorical. GeoTIFF files are written by default from Terra with this Ziv compression. And you could write your files out without the compression if you want read speed to be higher. As with any of these, the vignettes or the documentations are very helpful. And then a lead in to the next chapter. I think we all know R supports many static and also interactive graphic formats. The most general way to save a static plot in base R is to open a graphics device and create the plot and close it, and it'll write out that file as a PNG or a PDF, bitmap, JPEG, or TIFF. They mentioned briefly TMAP has TMAT save, and for interactive maps, there's MapShot, but quite a bit more on mapping techniques and how to manipulate maps and create maps is covered in the next chapter. This is just a placeholder to say that besides your say geospatial shapefile or raster file, that your images, your visual outputs can also be saved in the package or in as a file. Okay, in the 13 minutes we have left, I quickly walk through the exercises. I hope this is okay. They said first list 3 times a vector, raster, and geodatabase formats. We mentioned the Esri shapefile, SHP, and AMLs, the Google Earth. And when it's zipped, I think when you request it from Google, it comes as a KMZ. A GeoBuff is also a single file format, an FGB that is a geospatial format. Over in the raster side, geotiffs are pretty common. They get kind of big. ARC ASCII ASC files have a sort of a header and a list, much like a CSV file would have. There exists a geospatial PDF. Let's see, geodatabase formats. They mentioned this, that there is a SQLite container for geospatial objects that are a geospatial database when you encounter something like that. The question here in SF about the difference between read SF and ST read. Simply the read SF always has quiet is true, strings as factors is false, and as Tibble is true. So read SF is ST read with these 3 other default parameters.
Well, one stuff to add is read SF is kind of tidy compliant.
Ah, yes. Yeah, good point. Good point.
Yeah, it's exported always a table, and also like if you use reader, read CSV, read it's follow the same syntaxes. So this is so another, I mean, small differences, but it's for teaching it makes sense. So
Yeah,
you
good point. Okay, then they say read the cycle hire, sample data from SP data. So as we did up above, I made a system file pointer and then read it in, and well, in this case, it just did read CSV, so it would tell me what the columns were. Okay, then it says download the borders of Germany using our natural earth. This is so easy. So just say country equals Germany, and then write this new object as a geopackage format file, and this is the ending. So write SF knows to write it as a geopackage file with that DSN. That I think it's destination. I'm not sure. Okay.
I think
And then,
but I think also, but I could have been wrong all my life.
oh, it's all good. And then download the global minimum monthly temperature with a 5-minute resolution from geodata, extract the June values and save it as this TIFF file. And hint is to use subset. So here geodata has a retrieval function called world climb global, where we can get the minimum temperature at the resolution they call out, 5 minutes, and we pull that into a temp path. It takes a while to run. We get this file in the temp directory, and then I run Terra subset on the file we just downloaded, and give the layer name. This is the underlying layer we're interested in, and then we write that as a file tmin June TIFF. So we've used subset and then write raster to write that file up. Next question, a static map of Germany's borders. Here again, we did this before, we grabbed Germany. I just assumed a PNG file. Yeah, save it to a PNG. So I used the base R way of setting up the PNG, plotting it, and then shutting off the device, and it writes the file down to the local directory. And then the last one I was a little hung up with. I'm going to say eval equals false when I push this, but my map set doesn't work. But the intention here with the cycle higher points is to read that guy and present that as a save it as an HTML file with the cycle higher data sets on a web page. Okay, I'm gonna stop
The code
sharing.
seems fine. I'm not sure like the containers, I mean the GitHub action can write. Can it?
Well, you made a good yeah, when you use a GitHub action, I think you'd have some problems. You'd have to go to something like Docker and have a container to do some of these.
I don't know,
right?
but that's my first guess. Maybe not the correct one.
I know to pull from a geospatial database, I'd put the secret or the token
the vault
in GitHub, and it'd be happy to pull from it like SQLite and use that in a mapping context. But you're right, pulling a large file and extracting a part of it is probably too much to ask of GitHub Actions.
I don't know. This is my guess, but anyway, good job on the exercise.
Yeah, I'm going to stop sharing and look at the chat. I've not seen any chat. So there's a OSM tutorial, fantastic. And yeah, the Google API it used to be free.
Yeah, until like 5 years ago, I think.
Yeah, fantastic. And then layers of GeoPackage. Yeah.
Yeah, and I think shapefile have been around from like at least the white papers from the 90s. I don't remember exactly when it is, but yeah. And yeah, that's it. And yeah, is it in meters? Like my question was about your buffer. I don't know what was the unit in the world data set.
I'll go back and fix that. I was surprised to see it. It worked at one time.
This was always like, you know, the trap we fell on. No, good job. I don't know if it was a question, remark first, maybe.
No, I would just say good job too. I find it so fascinating. I'm still going through chapter 4, trying to really, synthesize all that information. But I look forward to getting to the rest of this. Yeah, I guess I can put on my video for this one. But anyway, no, I mean, I think it's so interesting, and there's so much to learn with all of this too, but the foundation is there, and I think it's really, really cool. I was only going to mention too, Femi, who's on the call here, is also facilitating the data visualization with our book club at the same time as this one. And just this past week, I guess it was yesterday, actually, we did chapter 6, which was about maps, and got familiar with ggmap and some of the other functions there. And so I guess so there's exercises in those chapters, and maybe there's a way to also use these concepts, execute those exercises using the concepts that are here within geospatial. So anyway, I was interested to see the crossover between those two. But yeah, there's so much to learn is what I'm finding out.
No, it's good. Yeah, definitely there is crossover. We'll see next week with Derek. So I think the author tend to use more TMAP, but both of TMAP and ggplot use the same grid object system, which is not the same than the plot-based function, which is used more like the pen mappers whole system. But yeah, so they're definitely like crossovers.
And can I ask a silly question? When we talk about resolution on these that you were going through, Jim, and you were talking about it in terms of minutes, 5 minutes, 10 minutes, that's like a division of degrees, right? Degrees and then minutes and then seconds. That's that context.
Yeah, a portion of an arc. Yes.
Okay.
Yep.
That's what I thought.
Yeah.
Yeah, I know good old GDAL can be frustrating sometimes because it's a library of library. And even like, because when you are installing it, you are basically install a bunch of library, take a lot of time. That's why SF is so big as a package, because it came also with it sometimes. But it's frustrating, but you have to get in, and it's sometimes difficult. But it's very powerful, and we have a lot of file formats. Sadly, it's kind of like the result of 40 years of work in academia, industry, and yeah. So it's, but GDAL is just simply awesome because like it allows us to work with all of this heritage, good or bad, new techniques also. So if sometimes you feel frustrated with GDAL, remember like my generation when I was 20, I had to move from one computer to another computer to use a proprietary software to transform a file into another stuff, plug it into a clear USB, go to another computer which have the correct license. And so thanks to that, now we can all work with one computer. One other note that's maybe is because like SF is so powerful, and the read SF and write SF are very powerful. They kind of use either DBI engine, which is like if you wrote to a PostGIS databases, you can use we have basically two options. Either you use GDAL, which is used like a string, like PG to semicolon something like host, like it will write the string that you connect to the databases, the old classic stuff, and then it will use GDAL. And if you use DBI, which is like a database instances in R, it's an R package that use a connection file to simplify that, it will use it. And I have found sometimes that the DBI package does not recognize a geometry type, which is very particular. I know we are speaking like very specific PostgreSQL, I don't know, jargon, but yeah, basically SF handled that well under the hood, so you do not have to care except in some particular cases. That's it. So be careful if it happened to you. It's well documented. You can use both because like SF use a lot of engine behind the hood trying to make your life easy, but sometimes reality is harsh. You need to specify like, I want this one. That's it. But yeah, it's awesome and powerful. Like, and before, like we were so yeah, all of these formats was proprietary, and still a lot of them, like you didn't mention, like, so geo package is like the OGC comply, I mean, open source format, but you have like S3 use geo databases, which GDAL also has, but it's doing through reverse engineering. They did not provide the actual codes. So it's a lot of work thanks to the people maintaining GDAL and doing this work and allowing us to work. That's it. That was my last.
Okay, we'll see everybody in a week.
Yeah.
Then.
See you, everybody.
Thank you all.
Bye.
Yep.
Thanks.
Bye-bye.
It was great.
All right.